planning. And I just want to introduce the first speaker, which is Adonis from Australia. He obtained his bachelor and master degree in electrical engineering from the University of the Philippines. And he has now just submitted his PhD thesis at the University of Sydney on planning for flexible future grids under power injection diversity. So since it is very odd times for him, he will be available for answering questions, but we will play the video with this presentation. So therefore, Linyu, could you please start the video? Can you hear me? Ah, great. Okay. Thank you.
The work I'm presenting is part of my PhD research with Professor David Hill and Professor Jin Ma at the University of Sydney. In this work, we motivate the integration of grid flexibility in transmission expansion planning to enable future grids to host more power injection diversity. We build on previous work that uses a new framework that measures and minimizes grid inadequacy based on the DC power flow in feasible set. The future of power grids is uncertain, but trends indicate the integration of many different players that interact together. This includes conventional dispatchable generation, intermittent RE generation, flexible and inflexible loads, as well as energy storage that can schedule both positive and negative power injections. A market setup is also possible where different market players control these assets. They can change strategies in both the long term via bilateral contracts or in the short term in spot markets. These developments will result in increased power injection diversity in the future. It makes sense to have a flexible or dispatchable grid, where grid operators can control power flows by deploying grid assets such as line switches, series compensation, and phase shifting transformers. To be able to design such a future grid, we need decision support tools that can integrate grid flexibility in transmission expansion planning. In existing tools, the objective is usually to minimize cost or maximize welfare, and usually only the RE and load uncertainty are modeled, with the rest of the generation assumed fully dispatchable, ignoring uncertainty due to market interactions. These modeling assumptions prioritize service continuity, so there's nothing wrong with this, but in the future, some grid operators may want to explore other expansion options that cater to more diverse power exchanges with little discrimination to promote grid access equity. In the previous work, we proposed to directly minimize grid inadequacy for power injection diversity instead of minimizing costs under different scenarios. This different approach allows grid operators to find grid expansion options that may be overlooked by other tools. In a previous work, we only consider finding optimal line additions so that we can improve a grid's inherent ability to host power injection diversity. In this work, we integrate grid flexibility in the form of line switching using the same framework that directly minimizes total grid inadequacy. To implement this framework, we first need a way to measure grid inadequacy for power injection diversity. In a previous work, we motivated the use of the power flow in feasible set for this purpose. To illustrate, we can visualize the DC power flow equations using the illustrations in the right. The top right figure is in P space or the power injection space. In this space, there's a bounding box defined by the bus power injection limits. This box contains a hypersurface of valid power injection satisfying the power balance constraint. Points in the hypersurface are projected in F space or the line power flow space using the DC power flow equations, where it intersects another bounding box defined by the line capacity limits. Some portions of the projection fall inside and some fall outside of this bounding box. Points outside of the box means that one or more lines is congested and that the power exchange is infeasible. These points comprise the power flow infeasible set, and the larger the size of this set, the more inadequate a grid is to host diverse power injection conditions. Without any form of power flow control intervention, the infeasible set describes a grid's inherent inability to host power injection diversity. In a previous work, we reduced this inherent inadequacy by adding strategic lines to the grid. In this work, we co-optimize line switching and line addition to further minimize the infeasible set. Here's an illustration for a 3-bus 3-line grid where bus 1 is a generator only, bus 2 is a combination of load and generator, and bus 3 is load only. The figures on the right visualizes the infeasible set in reduced F space. The diagram shows the line capacities in red, the feasible loading ranges in gray, and the infeasible loading ranges in black for the base case and for 3 expansion options. From the diagrams, we can see that there are infeasible power exchanges in the base case. This happens in the following cases. When the total load exceeds 1.5 per unit, the generators in bus 1 cannot be dispatched at full capacity because of network congestion. To supply the load, generators in bus 2 need to be dispatched, which may be more expensive or more carbon intensive. Interventions can improve grid access equity, like adding a new line 1-2, a new line 1-3, or a switch 2-3 to enable the full dispatch of generators in bus 1 or a shared dispatch in bus 1 and bus 2. These interventions either provide additional capacity, as in the case of line 1-2, or reroute power flows in the grid to enable feasibility of previously infeasible scenarios, as in the case of adding line 1-3 or switch 2-3. Either of the 3 interventions completely remove the infeasible set in this example. The loading profiles differ, however, with limited capacity margin when line 1-3 is added or switch 2-3 is added, as shown in the circled areas. Detailed multi-objective analysis will be needed to choose between the 3 options. It is easy to find grid expansion options that minimize the infeasible set for a small test system like this one. It becomes a combinatoric problem for larger test systems. There are different approaches to find grid expansion options that minimize the infeasible set for larger grids. In this work, we adopt the following scenario-based framework. First, we define a pool of power injection scenarios to represent the power injection space. Then, we minimize the infeasible subset by finding optimal line and switch additions. Detailed analysis can then be performed in later planning stages on these shortlisted solutions. We limit the scope of this work to step number 2, where we present a mixed integer linear programming model that co-optimizes line and switch placement that directly minimizes the size of the infeasible set. The objective of the MILP model is to minimize the size of the infeasible set given by the number of scenarios in the scenario pool that has network congestion. The constraints include the DC power flow equations, like the nodal power balance constraint, and the line flow constraints with and without switches, and with and without the new lines added. The next set of constraints solve for the amount of overload in each line and checks for congestion in each scenario. The other constraints define a reference bus and sets a limit on the number of new lines and switches, as well as some other miscellaneous constraints needed in modeling. As we mentioned earlier, the purpose of this model is to find line and switch additions that best minimize the size of the infeasible set. It is not meant to replace existing methods, but rather complement them in finding other options that planners may find interesting in later planning stages. Because the objective directly minimizes grid inadequacy, the solutions found may be good candidates for promoting grid access equity. Unlike other models that integrate generator dispatch in the optimization model, this approach fully decouples the scenario selection step. This has two advantages. One, it provides greater control in defining the scenario pool. And two, it provides transparency in what kinds of power exchanges are considered in planning that stakeholders can comment on. To define the scenario pool, however, grid operators must balance adequate space representation and computational tractability. To illustrate, we use the model in two test systems. Here are the results for the 6-bus grid. To generate the scenario pool, we sample from the entire loading range of each line, then use k-means clustering to limit the scenarios to 50. The figure shows the lowest number of infeasible scenarios that can be achieved for a given number of lines and switch added. From the figure, we can see that adding more lines and switches decreases total grid inadequacy, where the change in the size of the infeasible set with and without line switching can be used as a measure for added grid flexibility. In the base case, 84% of the scenarios in the pool are infeasible. If only a maximum of 3 switches can be added, this can be reduced to 78% as shown in the large orange rectangle. If a maximum of 3 lines can be added, the number of infeasible scenarios can be reduced to only 4%. But as indicated by the orange arrow, the same level of adequacy can be achieved with just 3 lines and 3 switches. This means that we can potentially defer the construction of one new line if we integrate line switching and line addition under one optimization framework. We can observe the same results for the 118-bus case study, where we can also observe a decreasing number of infeasible scenarios with more lines and switches added. In the base case with no lines and switches added, the percentage of infeasible scenarios is 88%. This can be reduced to 76% if a maximum of 2 switches can be added. If a maximum of 3 lines can be installed, the percentage of infeasible scenarios can be reduced to 62%. But if we combine line and switch addition, we can reduce the percentage of infeasible scenarios to just 60%, as indicated by the large orange arrow. Like the results for the 6-bus case study, this example shows how we can defer the installation of one new line if we can combine line and switch addition under one optimization framework. In summary, we have presented the framework for integrating grid flexibility in transmission expansion planning. The framework is based on our previous work that uses the DC power flow infeasible set to measure grid inadequacy for power injection diversity. We then presented an MILP model for finding grid expansion options that directly minimizes the size of the infeasible set. Case studies using the presented model motivate the integration of grid flexibility in transmission expansion planning. Future work includes other approaches in finding grid expansion options that also directly minimize the infeasible set. If a scenario-based approach is used, appropriate scenario space sampling and tractable optimization approaches are needed. Application in large and real-world grids is needed for further study. And finally, multi-objective decision-making tools must be developed to be able to compare between shortlisted options. This ends my presentation, and thank you for listening.
Okay, thank you very much. So as I said, this was a pre-recorded presentation. We have 4 minutes left for some discussions. If I look here into the question and answer chat function, I have no Ah, there's just one. No, two. I need to read them, of course. So maybe my co-host, could you give Patrick Pankiatiki the mic so that he could directly ask his question? Would that be possible? Hello, where's my co-host?
I'm here. I'm here.
Okay.
I'll do it. I'll do it.
Okay, please. So Patrick first, please.
Yes. Good morning. So you can hear me?
You should go closer to the mic, Patrick. You're very...
Okay. Sorry.
That's better now. Please go ahead.
Well, yes, interesting presentation. Thank you. And my question was, do you think that the current market design gives the right incentive to implement this kind of smart solution? NMP pricing require convexity seem not very compatible with this kind of idea. Could you comment on that?
Yeah, sure. So recuperating the investment cost would be an interesting problem to look in the future. But I think there's also inherent value in providing grid access equity. So how do you value that in terms of money? May be difficult, but I think it will be increasingly more important in the future.
Okay, thank you very much.
Thank you.
I have one more question from Keith. I can just read it. What steps of approximations do you think you could make to enable analysis of real systems, so real size systems, I think he wanted to ask.
Yeah, the examples presented here are just proof of concept for small test systems. So I think it's applicable in some of the smaller test systems, like in the Philippines, where it's just essentially an island. But for larger test systems, it would be difficult to sample many different scenarios. And what we did in this work is, instead of sampling in the power injection space, we sample in the line power flow space, where we select different line loading levels and then find representative scenarios that result in those line loading levels. And this approach may result in representing the space without looking at the different combinations of power injections, which I think may be larger than looking at the line power flow space.
Thank you very much. And the last question from Mr. Rahul Gupta, maybe for a short answer. How do you model the PNF space and why should it be a box?
The box representations is a direct consequence of the DC power flow being a linear model.
Okay, I see.
Yeah, so the linear transformations inherent in the DC power flow results in those modeling.
And do you feel happy with using the DC power flow approximation, knowing that you are on the wrong side, on the unsafe side?
The intended application of of this work is in the planning process. So I think it's common practice to use the DC power flow approximation because we're looking at 10 years, 20 years time span, and it doesn't make sense to go into that much detail into AC modeling in those time spans.
Good. Anyhow, thank you very much.
Thank you.
We have no time for further questions. I'm sorry, I had 3 more, but I think we have to proceed in order not to run out of time for the last speaker. So therefore, I want to go to the second paper.